Thank you, Josh, for the introduction and for the invitation. I have to admit I was a little bit nervous of this talk, but seeing so many familiar faces, some people that I know through Twitter, through conferences, through emails, at least two former teachers during the European Doctoral School of Demography, I feel a little bit better now. So, well, thank you for the introduction and for inviting me to share my research. I am very thankful and honored for this opportunity. If someone had told me 5 years ago when I was beginning this demography career that I would be presenting my research in a department with such a rich history of doing formal demography, I would not have believed it. But also, to be honest, I would not have believed anything that is happening this year. So I'm really thankful that I'm here able to present my research. Berkeley demography has been very inspiring throughout my short career when reading articles from former faculty and also faculty members nowadays, but also with recent graduates, PhDs, including Monica Alexander, who are setting the bar so high. I'm a fan of their work, so thank you so much. So the title of my talk today is Leveraging Formal Demography to Understand Lifespan Inequality Trends. I will be showing part of my doctoral work, but also new areas that I am working on and that I find exciting. And so I'm very happy that this is a core demography audience. Nevertheless, I will begin with explaining the key concepts that I will be referring to during this talk. So this graph shows the distribution of ages of death for British females in 1922 in the red line and in 2016 with the blue line. So we can see, for example, that in 1922, over 6% of deaths happened in the first year of life, while in 2016, it was less than 1%. In 1922, the proportion of deaths happening in ages less than 60 years was also significant, larger compared to contemporary UK. As a result, there has been an increase in life expectancy at birth of 24 years from almost 59 to 83 years. During this period, there was also a shifting of the mortality curve towards older ages and also compression of mortality around the mean. So for example, the shaded areas here represent 50% of deaths around the mean. The age range at which these were occurring decreased by more than half during this period from 30 to 14 years. And lifespan inequality basically refers to these changes in dispersion, meaning that more variation means increasing lifespan inequality. Now, life expectancy as an average mortality indicator conceals variation in length of lives, which is substantial. Therefore, lifespan inequality also is an indicator that complements life expectancy. So just as economists, for example, complement GDP per capita with the Gini coefficient of the income distribution, demographers too acknowledge the importance of complementing life expectancy with lifespan inequality. So I cannot, okay. So if you have, I can see everything together. I can see the chat, but if you have any question, just feel free to interrupt me, please. On that line, okay, so just as economists complement GDP per capita with the Gini of the income distribution, demographers too acknowledge the importance of complementing measures such as life expectancy with measures of variation like lifespan inequality. And I think it's important to do this because lifespan inequality reflects uncertainty in length of life at the individual level, and it also shows how health improvements are unequally shared at the population level. So over the last 15 years or so, there have been several important papers documenting the negative association between life expectancy and lifespan inequality, including those from Brian Edwards and Tulja Purkar in PDR, and the seminal papers by Christian Munden and Jaron Smith and Jim Bopel and colleagues. So for example, this graph here shows life expectancy at birth in the x-axis and lifespan inequality in the y-axis using data from the Human Mortality Database. It depicts how higher levels of life expectancy usually correspond to lower levels of lifespan inequality. However, I wanted to look deeper into this association during my PhD, and upon closer look, we are beginning to see this relationship reversed. This graph, for example, shows yearly changes in life expectancy in the x-axis and yearly changes in lifespan inequality in the y-axis for Central and Eastern European countries from 1960 to 1988. So the gray dots represent the expected hypothesis of an increasing life expectancy being followed by a decreasing lifespan inequality, while the red dots correspond to the unexpected increase in life expectancy with an increase in lifespan inequality. And the blue dots are just highlighting Russia. So during this period, we can observe that more than half of the time, life expectancy moved against the expected hypothesis. And we know that Central and Eastern European countries are usually treated as outliers from the human mortality database countries because they have mortality dynamics very differently from Western Europe. And one of these dynamics that highlights the importance of looking at variation is the association between life expectancy and lifespan inequality.
Jose, could you use your mouse just to show us the direction that you think this cloud is going and which one the last graph showed?
So this one here?
So this one shows, yeah, I guess a negative relationship. Is that?
Yes, exactly.
Okay. And then on the next graph?
So in the next graph, this is yearly changes. So I'm looking here at first differences rather than the levels.
Okay.
So from the previous graph, the hypothesis here would be that an increase in life expectancy should be followed by a decrease in lifespan inequality. So these two quadrants.
Okay.
So the gray dots. And what we found is that when we look at these countries that have such atypical patterns of mortality improvement over time, we see that over half of the time, the dots are actually concentrated in the other two quadrants. And we found in this paper with Alison Van Raalte that most of these dynamics were driven by offsetting effects of mortality change. So while there were improvements in infant mortality, there were very high and worsening mortality in midlife mortality, causing that even though life expectancy might increase, also variation was increasing.
And then why is this centered around 0 in terms of annual changes in life expectancy? I would have thought that most countries are improving.
Yes, not Central and Eastern European countries. So actually so this is only Central and Eastern European countries, and these countries between 1960 and 1980 had basically very small improvements in life expectancy.
I understand. This is not all of HMD. It's only the Central and Eastern European.
Yeah. This is not all HMD. This is only the Central and Eastern European countries.
Thank you.
Similarly, I mean, this reverse relationship has been documented in disadvantaged subgroups in different countries. So here I show the main results of Alison Van Raalte and colleagues paper published in Policy Forum of Science. And basically here the take-home message is that even though most subgroups, low, medium, and highly educated females in Finland were increasing life expectancy, except in the last period for the low educated women, we can see that lifespan disparity was consistently increasing since the 1970s for this low educated subgroup. And there have been other studies highlighting these reports, for example, from Denmark, the USA by Isaac Sasson, Scotland by Rosie Seaman and colleagues, and then recently also in Spain by Iñaki Permanier and colleagues. So one of the questions that I had, and my main motivation to approach my PhD dissertation was, can we use and develop formal demographic tools to understand these trends and differences? And my main motivation to approach these questions was that it seemed to me that we knew a lot about life expectancy, but we knew less about lifespan inequality. For example, this graph shows the world record life expectancy since the 1840s based on the seminal paper by Jim Oppen and Jim Boppel. And we know that they increased linearly over the last 200 years. We also know, for example, how to decompose average mortality indicators such as life expectancy by ages, by causes of death, using Arriaga's methodology, how to decompose them in compositional effects and so on. But we do not necessarily know how to do that with lifespan inequality indicators. So, for example, based on influential work done by Jim Boppel and Vladimir Kandas-Romo from his PhD thesis, we know that if we take the derivative with respect to time of life expectancy at birth, then the change over time of life expectancy is given by the integral of rho, and here rho represents the rates of mortality improvements, and these weights. And these weights are given by the hazard times the survival function, which is the H at the distribution, times life expectancy at hx. Now, for simplicity, I'm just going to call this raw times some pink weights, and these weights will be pink throughout the presentation. It's just to remind us that these are the weights of life expectancy. The key take-home message from this equation was that the change over time of E naught is a weighted total of rates of mortality improvement. And this was published in Demography in 2003 by Jim Boppel and Vladimir Canodas-Romo. Now, there are many indicators. So I wanted to see whether we can also find these kind of expressions for lifespan inequality indicators. And there are many indicators to measure lifespan inequality. There are measures of absolute inequality, including the variance, the standard deviation, or years of life lost. And there are also indicators of relative inequality, including, for example, the coefficient of variation, the Gini coefficient, and the Lifetable entropy. During this presentation, the first part of this presentation, I will focus on work done about the Lifetable entropy, because I think is very appealing for demographers, and also because, I mean, people that have inspired my work have also focused on lifespan, on the Lifetable entropy, including, for example, Nathan Kifitz. So this is the Lifetable entropy. Now, the Lifetable entropy, the first paper that we could find, and I have had discussions about this with other demographers, including some now in the audience. It was initially posed by Lesser in a Pop Studies article in 1955, but is often attributed to Nathan Kifitz in the 70s. Nevertheless, later on, Nathan Kifitz and also Lloyd Demetrius did a lot of work, substantial research on this type of indicators. Then in the 80s, a set of demographers, including Jim Boppel, Noreen Goldman, who was Nathan Kifitz's PhD student, and Graham and Lord, worked on this topic, further developing formal demography. And they found that the numerator of this expression here can also be written like this, where D of X is just the H at the distribution times E, the life expectancy at HX. And more recently, in 2003, in that paper in honor of 19th birthday of Nathan Kifitz by Jim Boppel and Vladimir, they just put a name to it. And they put a name to the numerator, and now we see this often in papers of formal demography called E-dagger. And what E-dagger represents is the average life lost at death, and it is a measure of absolute lifespan inequality itself. So for example, if someone dies at age 20 and their remaining life expectancy was 60, they contribute 60 years to lifespan inequality, or to the average life lost. Now, the interest on analyzing changes on this indicator of the Lifetable entropy led a couple of Mexican demographers to find this beautiful equation. So Oscar Fernandez and Iran Beltran Sanchez led to this equation that basically says that the relative change over time in the Lifetable entropy is given by the relative change in E-dagger minus the relative change in life expectancy. So from this equation, we know this guy here. So we know how does the change over time of life expectancy looks in terms of rate of mortality improvements. So me, together with other colleagues in Denmark, set out to try to develop an expression similar for changes in E-dagger and the Lifetable entropy. By finding the one for E-dagger, we might be able to complement the one for the Lifetable entropy. So together with them in a formal relationship in demographic research, and partly in the PNAS paper, we showed that the change over time in E-dagger is given also by the product of rates of mortality improvements times the pink weights times this function in orange, where H of X is the cumulative hazard and H bar is the entropy from HX. Now this function, I'm not gonna get too much into it, but this is the same function that was used by Sang and Boppel in 2009 to prove the existence of a threshold age. And this threshold age, what says is that improvements above certain age actually increase inequality, as opposed to what happens with life expectancy. So life expectancy, no matter where we do the improvements, we will always increase it. But in terms of lifespan inequality, there's an age above which improvements are translated to increases in lifespan inequality. Now, for now, I will talk more about this threshold age in a few slides. But the key point of this equation is that the change over time of E-dagger is also a weighted total of rates of mortality improvements. And we arrived to this expression together with Jesus, who is also in the audience, and also Peter Wagner from the Max Planck Institute in 2010. So going back to our original equation on changes over time of the life table entropy, which is what I was interested in, we now have all the ingredients. We have the changes on life expectancy. So we know this guy here, and we also know E dagger and how it changes over time. So we can plug them, the equations that we had in terms of rates of mortality improvements, and we arrive to this equation here. No? And this equation, again, what it's saying is that the change over time of the life table entropy is given by the total rates of mortality improvements times the same weights that we have been carrying along of life expectancy times a new set of weights. And now for simplicity, I'm going to call this product just G of X. And what I think is the key point of this equation and what we finally arrived to is that the change in the life table entropy can also be expressed as a weighted total of rates of mortality improvements. And well, you might ask me, so but why are you doing that? Why would you be interested in that? And is that this, by disentangling the rates of mortality improvements and then analyzing the weights, it's actually very easy to interpret changes over time. So for example, in this graph, I show the pink W. So these are the weights of life expectancy for Swedish females in various periods. So the first observation, which is very intuitive, is that improvements in mortality are always translated into increases.
It's a little bit small for us, so please use your mouse to point to what you're talking about.
Okay, so I'm focusing on this graph here, and so these are the pink W. So it's just how the weights look in different periods for Swedish females. So starting from the 1750s to contemporary Sweden. And the first observation, which is very intuitive about this figure, is that mortality improvements are always translated into increases in life expectancy. Therefore, these weights are usually or always positive. Secondly, these weights also represent how much life expectancy is gained, for example, by reducing 1% mortality at some age. So we observe, for example, the importance of infant mortality. So here, no, the light pink line, we can see that that pink line at birth goes up to 8. So that means that by making a very small change of improvement in infant mortality back in the 1750s, life expectancy was increased by a lot. Similarly, we can see that how females in younger ages, improvements in mortality at these ages were also translated into substantial gains in life expectancy. In contrast, we can see that the darkest line, which refers to 2010 and 2017, by reducing 1% of mortality in infancy is the same as reducing 1% of mortality at age 63 or so, or more or less.
Jose, can I interrupt?
Yes.
I have two questions. The first one is you're talking about improvement. So is it improvement over the period you're looking at? So for like the very light pink, it would be improvement between 1751 and 1759.
Yeah, so what I'm showing here is the weights. No, so from the previous equation of the, sorry. So these weights is basically how would life expectancy react to a small change in mortality.
But is that an average annual change?
Yeah, so this is taking from the 10-year, from an instantaneous point of view. So we take one life table, and I took 10-year life tables from the HMD. Okay,
and what's the difference between this and the decomposition method by Begun, Shkolnikov, and Andreev?
So you mean the stepwise decomposition method?
Yes.
So the difference is that, so the stepwise decomposition method, which I will also address a little bit later, is similar, but for this particular method that we're using now, we don't need 2 points in time. We're just inferring how much life expectancy would react based only on one table, as opposed to the stepwise decomposition method that you need for example, 2 years, and then you can decompose the difference. And their algorithm is basically just replacing a small value, each one of the life table values, and then see how much it changes the life expectancy. That's how the stepwise decomposition works a little bit, the algorithm. So I think in terms of operationalizing this framework that I'm showing, we could also do it with the stepwise decomposition method or with the Oriuchi method, for example.
Okay, so here you're saying, you're looking at every age and you're saying, if we reduce the mortality rate, or I don't know what, by the same proportion for every age, how much difference that's going to make to life expectancy at birth. And so if you have very high rate of infant mortality, it's going to have a much larger impact than a small rate. Is that right? That's
Yes.
The intuitive way to understand it?
Yes, correct.
Okay.
I see another question by Josh.
I'm sorry, yes, I don't expect you to read these questions. I know it's very hard to read the questions while you're presenting. So I'll interrupt you if I want to ask it. Is that okay? I'm just writing
Okay.
for future things.
Okay, yeah, perfect.
Don't worry about it. Thank you, Magali, for that question.
Yeah, so these weights are also somehow reflecting the mortality stage at which these countries were. So obviously in 1750s, like, infant mortality was very high in such a way that by reducing just a little bit of infant mortality, you gained a lot life expectancy, as opposed to contemporary Sweden, where infant mortality is very low. Reducing a 1% infant mortality, for example, in Sweden today, it brings relatively very low gains in life expectancy compared to 100 years ago. So now in this figure and the one below, I show now the weights for lifespan inequality. So this is intuitively more or less the same interpretation. So how much lifespan inequality you lose by improving a little bit mortality in some age. So we can see the same importance of infant mortality on reducing lifespan inequality. And we can see, for example, that in today's Sweden, which is the darkest color, reducing 1% of infant mortality decreases lifespan inequality the same as if we reduce mortality at age 73. There are other features that we can learn from these weights. And one is not only that how midlife mortality is very important for lifespan inequality, but we can also see that there's an age represented here by the dash bars at which they go above zero. And this is what we call the threshold age. So above these lines here, when you reduce mortality, you actually increase inequality. And this can have important implications in modern developed countries where improvements are happening at older ages. So maybe that is why we're seeing this relationship between life expectancy and lifespan inequality being less strong than before. Now, another key aspect of this framework is that we can use it to pose different.
Could I ask you to comment on the connection between this picture and what we were seeing in Central Europe with that?
Yes. So for example, in terms of these weights for Eastern Europe that did not follow obviously the Swedish pattern, we could expect that the weights around midlife mortality would be very high, for example, for Russia in the 1980s, where midlife mortality is very high due to, for example, alcohol consumption, accidents, and also cardiovascular diseases. So I would expect for Sweden, this bulk here being much high, for Russia, for example, being much higher than for Sweden, which means that if you reduce or if you place your improvements in, for example, young males, you actually decrease lifespan inequality a lot. So that would be for the context in terms of Swedish females that went through this smooth mortality improvement, as opposed to, for example, Central European countries where there was a big period of stagnation, largely caused by deterioration at younger ages. So this framework, once we are able to disentangle the rates of mortality improvements with other weights, we can use it also to pose different scenarios. These are hypothetical scenarios. I'm not trying here to, in the next graph, to depict another reality, but I will tell how it was motivated. So this graph here shows life expectancy in the x-axis and it shows lifespan inequality measured by the log of the entropy in the y-axis. Each one of these gray lines refer to which year we are talking about. So for example, this is life expectancy in 1950, and this is also Swedish females. So the blue dots refer to what was observed. So these are basically the HMD points. And we can see that once we log the Lifetable entropy, there is a quite linear relationship between levels of life expectancy and lower levels of lifespan inequality. So we were interested in looking at this relationship, and we wanted to find out whether this was just mere coincidence, whether maybe it didn't matter where you place the improvements, you will always find this relationship, because it was strikingly linear to us. So playing around with this, with our framework, we came up with two extreme cases just to see how this relationship was going to change. So we have the youngest equality scenario. So this means that we're going to place improvements always at the lowest age at which deaths are still happening, in such a way that it matches the life expectancy in some period. So for example, I will start decreasing infant mortality. Then once there is no infant mortality, I go to age 1 and start reducing mortality at age 1. When there's no more mortality at age 1, then I go to age 2 and so on, but always matching the life expectancy that Sweden experienced. And then I have the other scenario, which is the red dots here, which is about constant change over age. So what would have happened if we place the improvements, the same improvements in all the ages, in such a way that again, life expectancy is matched yearly. And what we found was that constant change over age could have led to fewer equality on lifespans, matching the same levels of life expectancy observed, while the youngest equality could have reached substantially lower inequality. So in virtually every point between these lines is a potential value that the Sweden could have had. So potentially there could have been a lot of trajectories, and nevertheless, this is what we observed. So I think this points towards the fact that humans have been able to place improvements more or less good where it matters, but not optimally. Any question about this graph? I can make a pause now, just in case there are questions. Yes, Ilya?
Could you please explain what is the scenario youngest equality?
Yeah, so youngest equality is basically, so we start with the age-specific mortality profile of Sweden in 1750, and we're going to start reducing mortality from the youngest age. So we're going to make improvements first at age 0, and then once there's no more mortality at age 0, then we move on to age 1. And once there's no more mortality at age 1, we move on to age 2. So this is just a completely hypothetical, unrealistic scenario.
And is there evidence that this is the one that brings most equality?
So the most equality, I guess that would also depend in terms of how the mortality was in the beginning. No, but I mean, the extreme scenario for the highest equality is that all the individuals in your population die exactly at the same age. So then there is no inequality. Okay, so this was about how to develop a little bit of formal demography to understand lifespan inequality trends over time. But I also want to take the time to acknowledge other contributions to formal demography and also on studying lifespan inequality from this formal demography perspective. And firstly, there are these classical demography contributions with the seminal work of Tulja Purkar, of Lloyd Demetrius, Nathan Kifitz, Noreen Goldman, Jim Boppel, that they created the foundation of looking at lifespan inequality or variation indicators from this perspective that I'm talking today. Now, demography as a discipline has been also pioneer on the composition techniques. And more recently, there have been also new important developments on this arena to analyze lifespan inequality. And I will classify them in 4 big groups, and they don't intend to be exhaustive. Actually, if I'm missing someone, please feel free to let me know. So the first section that I have is there has been a new wave of interest on the sensitivity of lifespan inequality, on how lifespan inequality reacts to small changes in age-specific mortality. And here we can put the work from the population matrix framework from Alison Van Raalte and Han Caswell. And also let me just say that Hal Caswell can be put in any of these sections because he's done so much work that he can also be classified in the classical demography section. And also Peter Wagner and Tomasz Wryska from the Max Planck Institute. Then we have specific decompositions of lifespan inequality, including what I showed earlier, but also on the composite differences between population by causes of death. For example, the work by Claudia Nau and Firebow decomposing on the spread, allocation, and timing effects for the variance of the HAD distributions, where later on, Jesus, who is present here, did it for also the standard deviation. We have the work by Vladimir Shkolnikov and colleagues on the Gini coefficient, and the work that I talked about earlier by Oscar Fernandez and Iran Beltran Sanchez. Then we also have formal demography papers on finding these threshold ages. One of them is obviously Duncan Gillespie and colleagues who found this threshold age for the variance of the HAD distribution, Sangam Popel in 2009, but for the E-Dagger, and we recently published a paper on the Lifetable entropy and its threshold age. Now there are general decompositions, which are the ones that Magali was referring to. And these last have been very informative to analyze trends in lifespan inequality. So these are very similar. And the first one that I wrote here is the linear decomposition model, which was pioneered by Shiro Horyuchi and colleagues. Then there is the stepwise decomposition method by Andre Vetal, and also Hal Caswell has his Lifetable experiment decomposition technique. These last methodologies have been very informative to analyze trends in disadvantaged groups that I mentioned earlier, but also they have been very important to analyze recent stalls in life expectancy and increases in lifespan inequality in, for example, the USA and the UK. These trends have highlighted the importance of midlife mortality in recent patterns of mortality change. However, me coming from a developing country with high levels of premature mortality and also to a large extent due to violence, I see the need to also look at other countries and not only at developed countries. I think a lot of this research on lifespan inequality and long terms have been focused a lot on developed countries, mainly because the data is available. So I also wanted to go a little bit further and analyze other types of countries. So in the last part of the presentation, I will just focus on how to use these formal demographic tools to disentangle violence in the form of homicides and its effect on lifespan inequality. This research combines my interest in mathematical demography with more substantial part of my work, which has focused on quantifying the impact of violence on population health. Now, violence and lifespan inequality put together can be very informative because higher lifespan inequality underlies greater uncertainty in length of life, which can have important implications on planning events over the life course, such as when to study, when to retire, when to buy a house. It also highlights increasing vulnerability at the society level, and it also points to ineffectiveness of policies aiming to protect individuals. So for example, to answer these questions or to get into this topic, I pose 4 questions. And these are: how does lifespan inequality manifest itself in more violent countries? How does it compare with peaceful nations? How does this relationship compare between men and women? And what ages and causes of death are explaining the difference between violent and peaceful countries and also in trends over time. So I'm gonna talk about a little bit just the Mexican case. So in Mexico, this graph is the usual decomposition by ages and causes of death of life expectancy. So everything that is positive is contributing to increasing life expectancy, and everything negative means that they decrease life expectancy. So between 2000 and 2005, there was an increase of 10 months in male life expectancy. And this increase was largely driven by improvements in infant mortality, even homicides were helping to increase life expectancy. And the main driver of slowing down life expectancy was increased diabetes mortality. Now, in 2006, around 2006, there was a policy implemented in Mexico aiming at mitigating drug cartels operations. And what happened was this. So homicide rates between 2005 and 2010 more than doubled in Mexico, which led to a decrease in life expectancy of almost 3 months in this period. But homicides alone were reducing almost 9 months of life expectancy. And we can see that the most of the effect was concentrated at young ages. If we look at the regional level, if we look at the state level, for example, in Mexico, then the results are even more striking in some regions with, for example, Chihuahua, which is the northern state bordering with Texas. Male mortality rates in that state were 3 times, for example, the rates of the US troops in Iraq between 2003 and 2006. So obviously, homicide happening in premature mortality in concentrated at younger ages, it has a big impact on lifespan inequality. So
José?
Yes.
I didn't really understand what happened in 2005 that changed the situation. Can you give us a quick explanation? Thank you.
Yeah, so in 2006 began what is so-called the war on drugs, which is, I guess, I think is a bad name, but it's how it is called. So the president at that time implemented a policy that allowed army operations trying to mitigate drug cartels operations in 2006. And there are many explanatory factors on the increase of violence, but one of the main ones is that, in my view, is that if you try to decrease violence with more violence, I think what you're going to get is just more overall violence. And obviously the drug cartels had also more incentives to have more action, because while some army operations were mitigating some drug cartels, that created an incentive for other drug cartels to go to that area. No, and at the same time, the drug trade with Colombia being more or less stable and low, this also created an incentive for Mexican cartels to pass drugs to the USA, for example. So that's what created all this mess and this sudden increase and very sharp increase of homicide rates in Mexico in 2006.
Thank you.
Jose, about how many slides do you have left? We're at about 10 minutes to 1.
Yeah, so I think I have 5 or 6.
Okay. We're getting a lot of questions in the chat. So it's kind of your judgment how much you want to spend talking and how much you want to spend hearing questions. But let me delay you.
Yeah, so well, let me just finish with, so obviously homicides being concentrated at such young ages, it has a massive impact on lifespan inequality. So for example, this is the impact on lifespan inequality before 2006. So homicides were contributing to lifespan inequality, reducing it, which is desirable. So what happened in the following 10 years is this. And here, each one of these guys is a state in Mexico, divided by different regions. So we can see just a shift of the dynamics of the impact of homicides, and basically improvements made in 10 years were completely reversed in the following 10 years. And while this is similar results we found for Venezuela, made with Jenny Garcia from INET, and she is from Venezuela, and we published the results in the International Journal of Epidemiology. So this is the impact of homicides on increasing lifespan inequality. And this is just my current work, which is looking at this relationship of violence and lifespan inequality from a global perspective. And basically the main findings so far that we have is that consistently those countries with highest levels of violence have also the highest levels of lifetime uncertainty or lifespan inequality. So for example, the country with the highest lifespan inequality based on mortality data from the Global Burden of Disease, WHO, and so on, is Syria, which largely is caused by war-related deaths. So just to finalize, I know it's usual that the audience is the one asking me questions, but given this opportunity to show my work in such a department with rich history of formal demography, and I think Ron Lee is probably the audience, I dare to pose this question. So I was reading today as part of the of the program in demography in Oxford at the master's level, we give them to read Ronald Lee's Demography Abandoned Its Core manuscript, which starts with a little abstract, and it says that I think a staff member from the NICHD, I think is correct, that says formal demography is in a coma. Perhaps we should just let it die a natural death. And this was written 20 years ago. So now I dare to pose the question also to you. Where is formal demography going 20 years after this reflection? And I finalize with saying that I think the pandemic, the ongoing pandemic, has actually given a very important place to demography on explaining it. Several demographers have get into analyzing the pandemic and adding population structure to the conversation, death rates, the recent paper by George Goldstein and Ron Lee and PNAS. So where are we going? I think we might be actually in good ground now to move on with formal demography development. And that's it for me.
Wonderful, thank you. And thank you for jumping right to the conclusion, so we have plenty of time for discussion. Let me start out with Ron. Ron is asking about the conceptualizing inequality. Ron, do you want to just turn on your mic and ask your question?
Okay, I'll turn on my face too. I'm audible. I'm wondering about how this concept of lifespan uncertainty or inequality is related to the current discussions of socioeconomic differences or other gender differences or whatever in lifespan. And it seems to me it's a very different, this concept that you're discussing today is about ex post variation in age at death, whereas the discussion of SES differences is about ex ante differences. So that if there were no ex ante differences, then everyone would have the same life expectancy at birth, but we'd still have a large variation in the ages at which people actually died, since it's just probabilities at each age. So I guess that's my basic question. Could you say something about why what the interest in this kind of uncertainty or inequality in age at death is and compared to the other? Thanks.
Yes, thank you for that question. I think that is one of the key questions on any person doing this kind of research. Well, I think it comes into the conversation that usually those countries with higher socioeconomic inequalities in longevity tend to have lifespan inequality at the population level. So in that sense, lifespan inequality at the country level can be at least a hint of maybe a country experiencing larger inequality, like normal inequality levels in the inside. And one notable example is the US. Now, the USA achieves the similar level of life expectancy of, let's say, Sweden, but consistently with higher lifespan inequality. And among the developed countries, I would say that the USA is also one of the countries with high inequality in terms of socioeconomic inequalities. We see, for example, that consistently those subgroups with more disadvantaged, such as lower education or lower socioeconomic status, tend to have not only shorter life expectancies, but also higher levels of lifespan inequality. So I agree with you that they are not interchangeable, but I think they talk to each other more or less in the same line in terms of conceptualizing inequality from a more, like, I would say, classical sociological perspective.
How about integrating the two or decomposing the total into intergroup and between group?
Yes, so there has been, that's a very good point. I think Claudia Now and Fireball were precisely, and also Tulja Purkar and Ryan Edwards were interested on decomposing between and within inequalities. So I think one of the main findings of Ryan Edwards and Tulja was that within inequality explains most of the variance of the between differences among countries. But in terms of linking this with social inequalities, I haven't, well, I don't have at the moment in my mind a paper that has done this before.
Thank you.
Thank you. Maybe I'll just ask a question I saw on the very first slide, which was where you showed the density of death. It was from the period life table. And as we were talking, I saw that that was an important concept for looking at changes in period life expectancy. But again, conceptually, should we be thinking about equality as some measure of the period life table, or should it really be the cohort life table and we're just using periods because that's what we have available?
Yeah, so I have 2 points with that. So yes, we are referring to period life tables. We could do the same with cohort. Well, we have done with cohort life tables, and we found more or less the same of as life expectancy increases, lifespan inequality increases, and recently, working together with colleagues from Max Planck Institute and Vladimir, I don't know if you're familiar with this concept of the cross-sectional average length of life developed by Michel Guillot, which takes into account also the history of cohorts, but is a period measure. So we did something similar for lifespan variation. And again, this negative association is there. I think one important question on this is, how do we internalize, for example, uncertainty? Like how I would think that in Mexico, where we see a lot of young people dying, if you ask to someone like how long do you expect to live, they will tell you, no, maybe not very long, because they are comparing with their peers in a period basis. They are looking at different generation at one point in time. In that sense, I think that period measures are useful when interpreting this as an uncertainty of life, or lifespan inequality as an indicator of uncertainty. And in fact, there was a recent paper 2 years ago in Demography. So this subjective life expectancy is a well-known concept, but subjective lifespan inequality hasn't been approached that much. But in a French survey, they asked the interviewees, how long do you expect to live, or with what probability do you think you're going to survive to this, or like kind of trying to capture uncertainty. And the results were actually surprising, because what they say matches period life tables in France.
Great. So I think we have a few more minutes. If we could take questions from people who haven't asked yet. I think Dennis and Ilya may have questions. And if people have questions that they haven't entered in the chat, just go ahead and turn off your mic and we'll try to just do this without me calling on you. Total silence. Okay, just like doing a graduate seminar over Zoom. Okay, so let me just call on people. Dennis, did you have a question?
So I mean, I think my question was mostly answered. I asked a couple of things. Maybe one thing I was curious about was how, in the slide you showed towards the beginning with the analysis about inequality as a function of education, I'm curious how, this is sort of a minor point, how you address the fact that education happens later in life, and presumably a lot of inequality comes from death rates at young ages.
Yeah, so well, most of papers on educational attainment and socioeconomic status are usually conditioned on surviving to, for example, age 20 or 30 when education is finally finished. And most of them are also, a new wave of studies are also based on wealth. They use usually these countries like Denmark and Swedish data, where they have individual level information on the wealth and the socioeconomic status. So that's how they account for it. Even though it happens later in life, they take them as period measures.
Very interesting, thank you.
Let me ask maybe responding to your question about formal demography and asking you, so we're getting like we at Berkeley have this micro data project where we have individuals with demographic characteristics and how long they live. And I know you have registered data in countries like Sweden and Denmark. Is there any convergence of these kind of population aggregate concepts like you're working with in your formal models and micro level data?
Well, I think I would ask Ron Lee because it's more or less what he was reflecting. And there is also this paper by Francesco Villari in population studies on merging micro and macro perspectives. I see, yes, I see a convergence, but it depends a lot on the data. So the data at hand in Denmark, for example, definitely the individual level data, we can use formal demographic methods to test different hypotheses and to measure inequalities in different ways. So I do see a converging as also we develop more formal demography. I mean, we don't tend to use, for example, I don't know, a seminal decomposition method like Itagawa. We wouldn't use it with individual level data that so much, but I think a lot of concepts relating to the dynamics of different indicators can be used with individual level data. Like, I think what I showed today could be operationalized with individual level data in some way when disaggregating by many characteristics of the individuals, for example.
We can finish with a question from one of our first-time seminar attendees, and I'm going to pick on Monica, just making fun of her a little bit, and also on Xia Jiang from Stanford. Do you guys want to finish us off with a question?
I may have a naive question. Like in your last slide, you were asking how the formal demography will be in the next 20 years. And since I'm like only a PhD student, I'm also wondering the same thing. When I try to decide my PhD thesis in the future, I'm thinking, should I do more interdisciplinary research, or is demography has a promising future? Because my supervisor is Toja Polka, and he suggests me to try more interdisciplinary research, like try to combine demography with biology or ecology. Yeah, I just want to know, what do you think about this? And yeah, sorry.
Well,
sorry.
Well, I'm going to still answer. So again, from notes that I've read, but I would say demography at its core, I mean, is mathematical. Like we like to think about it, but it's also multidisciplinary and interdisciplinary in so many ways. So we draw not only on our theory, our mathematical theories, but we draw on sociologists, we draw on the statisticians, we draw on ecologists, on biologists. So the group, for example, here in Denmark, we do demography of primates, of animals, well, these are all animals, like primates, humans, other monkeys, plants, no? So I would say, if you're asking me whether you should pursue a career in demography, my answer is yes. But don't say to anyone after this call that I said that.
Thank you. Awesome. I'm also working on like other animals and plants. I think that's my first step.
And Xia Jiang, we're going to go back to Tolja and ask him about his recommendation. So don't worry, we'll get him on a future brown bag. Monica, do you have a question?
I don't really have a question. Thanks for a great talk, Jose. I guess I'm really interested in this idea about like, how do we think about these micro level data sets in combination with formal demographic techniques? And I was wondering, maybe you could comment, particularly, you know, as you're moving towards looking at measures of violence and how they're affecting lifespan inequality, how can we sort of combine micro level data sets that might measure individual level experiences of violence and sort of risk of violence with sort of these macro level measures of lifespan inequality? Like one sort of possible use of these sort of macro level formal demographic techniques is a data quality check, right? We expect a certain thing to happen based on, you know, maybe we can calculate, like with Sensoke, for example, we can calculate some measure of life expectancy, and then we can sort of compare that with sort of, you know, better data sources or aggregate sort of level data sources to check the data. Could you perhaps comment a little bit about how you could see the sort of interplay between, you know, these formal demographic techniques, potentially like statistical techniques at the individual level, as a way of sort of moving forward in the formal demography space?
Yes. Well, firstly, if I had to ask someone that, I would ask you. So, but I do have an idea. I think, no. So we are used to measuring life expectancy. We're used to measuring healthy life expectancy, which includes some biomarkers. We can think of limitations-free life expectancy and so on. I think the new wave of research in terms of lifespan inequality will come from health variation in healthy lifespans, variation in dispersion in, for example, limitations-free life expectancy and so on. I think that could be a potential way of mixing these biomarkers with measures of inequality or variation in general. At least I know that here in Europe, the group in Spain just got an ERC to basically just work on that for the next years. They are close collaborators with us, so I hope we will see more research on that front. And the other front is population matrix models. So Hal Caswell's framework can be used to measure, to include incidence biomarkers into different measures of variation of any statistical moment. And I have that very fresh because I saw today his talk. So so I'm just stealing again, just an answer from him. That's the future, I think.
Great, thanks.
Wonderful. Thank you, Jose Manuel, for a wonderful talk, and a talk that was very generative in terms of lots of people trying to push forward on what are the next steps. So we got a lot of, I think, ideas of ways that people would like to push this whole agenda, and I'm sure you're going to take up some of them yourself, and I hope others got excited to do the same. So thanks again for a wonderful talk and for staying up so late for us. We really appreciate it. We will be in touch, and thank you, everybody. We're not doing Gather Town today. We're doing a Gather Town break. And just a reminder, we are having a brown bag, our post-election brain detox focus on biodemography. Get out of the election space and noise in your brain and get back to basics with biodemography next Wednesday. So thanks, everyone from around the world for joining, and see you next week, I hope. Bye-bye.
Bye. Thank you, everyone.
Bye. Thank you, Jose.